Hey statisticians, we are looking at the last part of probability, z-scores and quantiles. Let's start by thinking about Frank, who took a chem and a bio exam, and he scored a little lower in chem, a little higher in bio. You can tell which one he personally did better in. But compared to the group in each of those, which one did he do better? Well, you could look at the difference between the means and see kind of which one he did better, but there's also another consideration, which is how spread out the data is. Here's the mean, and he's 6 points above, but this is pretty spread out, so maybe a lot of people are 6 points above and below. And this is, eight points above the mean, but it's a little less spread out. So which one did he actually do better compared to the groups? It's a little more challenging to see, and that's where z-scores come in. These are IA scores out of 20, and on average the red, the orange, and the blue curves all have the same mean. The green curve has a lower mean, but they all have a little bit of a different shape to them, right? And so like the blue, everything's kind of smushed together, has a smaller standard deviation compared to orange or yellow, whatever that is, which is much more spread out. And so this is like the percent of the students getting a 10 or a 12 or whatever. So probably if you were in the blue class, you have much higher probability of hitting that 10, where the orange class, you have a more probability of hitting an 18 than you do in the blue class. You have almost no chance in the blue class. In the orange, you have a little bit higher chance of getting an 18, but you also have a chance of getting a 2, so because everybody's very spread out. Where in the blue class, maybe everybody's been shown very specific restrictions on what you should do your IA in that will make sure you hit a 10. And so what's interesting about this is these are all normal distributions, but it's hard to compare them. Enter standard normal distribution. There's only one curve, there's only one parabola, there's only one logarithmic curve, and we just transform that, right? And so like this is the same curve, and we can make that look like that already fits pretty nicely there. But this one, if we did this again, we'd have to transform it rather aggressively to get it to sit in the right spot. And that's what a standard normal distribution curve is, taking an original curve that you have data for and turning it into a basic one that is the standard for everybody. We try to pick the easiest mean and standard deviation, which is 0 right in the middle, and a standard deviation of 1. And if we transform all of these into this curve, the red curve, then we can compare two sets of data. If you went with the same idea for the math IA score, you could say here's the mean, what on average people got out of 20, and you can see this curve isn't exactly how it should look, but you can see here that one standard deviation is 2 points wide, and sometimes that's hard to say, like if it's hard to know how much data is in there because we don't always know the standard deviation and such. And so if we take this and transform it from this curve into a standard normal's mean is no longer at 12, it's at 0, because then you can see positive numbers are above the mean, negative numbers are below the mean. So if we take that and transform it, slide it over, that's cool. But then also we want it to have a standard deviation not of 2, because that's a little distracting, right? Like I don't always know that this specific curve has a standard deviation of 2. It's nice to know, oh, this is a standard normal distribution, which means that the data's been manipulated a little bit so that one standard deviation is out at 1 and 2 standard deviations is out at 2, and then we can use the principles of a curve and say, oh, this must be 34%. If you're 1 standard deviation above, I know that there's 34% chance of being within 1 standard deviation. So this curve doesn't look exactly like I want it to, but we transform our data curves from what they naturally are into this standard, which has mean of 0 and standard deviation of 1. So what a z-score really does for us is it compares what values we have to the mean and in terms of standard deviations. So how many standard deviations is this point away from the mean? And that's easier to connect different data sets with and talk about how far away, how many standard deviations away is this point in this data set rather than this point in that data set. So let's go back to this one. If your score was a 16 and the mean was 12, in this case, a standard deviation, it looks like, is 2. So your 16 would have a z-score of 2 standard deviations. And it's because the difference between 12 and 16, your score, 16, minus the mean, 12, divided by the size of the standard deviation, that's 4 IA points, divided by 2 points per standard deviation, gives me 2 standard deviations away, which makes sense. Here's 1 standard deviation, there's 2 standard deviations. So if you looked at your z-score, which is like your standard, how many standard deviations are you above the mean? If you get a negative value, it means you're below the mean. And if you get a positive value, it means you're above the mean, and that comes in with this subtraction. Okay, so let's try it out. 30 students took the binomial expansion test, and mean was 5, standard deviation of 1. Franz Ferdinand's score is 6. How many standard deviations away is that? What's his z-score? Here's the mean at 5. Standard deviation is 1. So this must be 6, this must be 7. So Franz's score, if he scored a 6, he's 1 standard deviation away, so his z-score is 1, right? Ozzy Osbourne scored a 3, obviously, so since a standard deviation is 1 unit, this is 4, this is 3, so Ozzy's got a z-score of -2. Since this is a higher number, Franz is obviously doing better compared to the group. Play the same game with slightly modified numbers. Mean is 5 still, but the standard deviation is 0.5. So this is 5.5, this is 6, this is 6.5, right? This is 4.5, this is 4. Franz gets a 6. What's his z-score? Well, 2, because he's 2 standard deviations above the mean. You can use this idea and say Franz gets his x value is 6, so 6 minus the mean is 5, per the standard deviation is a half, 0.5. So his z-score is 1 divided by 0.5, that's 2. If you're not sure why that's 2, come see me, it's fractions. So Ozzy's score is 3.5, obviously, which is down here. So he is 1, 2, 3 standard deviations below the mean, so -3. If you weren't sure about that and wanted to do it mathematically, you'd say Ozzy's score minus the mean over the size of the standard deviation. This is
1.5 divided by 0.5. You can throw that in your calculator, or you can just turn them into fractions and divide. 1.5 is 3 halves. Half is 1 half. You invert and multiply, so 3 halves times 2 over 1. The 2's cancel out, you're just left with that 3. It's, this is negative, sorry, so that's negative, so that's negative, so that's negative, voila.
Okay, so again, Franz is doing better because it's a higher score, z-score, right? So he's doing more standard deviations above the mean. And this is a nice way to connect different data sets. Going back to Frank doing a chem and a bio test, this is the same standard deviation. What I'd like you to do is find the z-score, his z-score for both chem and bio. Pause me and try that. We looked at the z-score for these. We looked at Frank's score. He got a 67, and the distance between that and the mean is 6. And since this is about 6, this is 6 over about 12. So he's 6 points over the mean. Standard deviation is 12 points, so this should be about 0.5, and it is. It means he's about a half a standard deviation above. Same thing here. So he's 8 points above the mean. Standard deviation is 16 points, so he's exactly half half a standard deviation above the mean. So he's got a z-score of 0.5. So he's doing better compared to the group in chem, even though he has a worse score. So really, z-scores, if you keep them in mind of how many standard deviations above the mean is this, it helps make sense of the whole thing. Gus, probability. Probability, Gus. a quantile is a k-value. It's like a limit which bounds a certain percentage of their data. So for example, on the math exam, there's a mean and a standard deviation, and Mr. Wexler wants the lowest 20% to come into the ISFL summer school program. So what we can do with this is use the inverse function like we did. We want like a boundary that holds the 20% down, and so if in your calculator you want your x value to be less than k such that you get 20% of the curve in there, you punch into your calculator. Second distro, we want an inverse normal, means I want to give you the area and you tell me where that happens. I want 0.2, 76 and 8.2. And we get 69.1 points. So that's the limit, that's the bottom, almost 70 points to get you out of going to summer school. You're going to summer school. We can use that same trick if we don't know a mean or standard deviation. For example, 98% of ducks have wings shorter than this amount. So we can use the idea of the curve and find the standard deviation. We could figure out the quantile that bounds the 89% in a standard normal curve with 0 in the middle and 1 is the standard deviation. What does that look like? How many standard deviations away is that? You say second distor inverse normal. I know you can have a calculator later. And we want 98%, but we want to talk about the most basic curve, the standard normal. So mu is 0, standard deviation is 1. 2.05, that means that something that has 95% of the data in here, whatever that location is, will be about 2 standard deviations above the mean. We can apply that to our specific curve with the ducks like this. These ducks have a wings shorter than 60, so in our case 60 is this point. Our median is 50, and I know that's 2 standard deviations. So this distance between here and here, 50 to 60, that's 10 units, right? And I know that's 2 standard deviations, right? So that's 10 centimeters per 2 standard deviations. So that means there's 5 centimeters per standard deviation. So that's the size of our standard deviation. If you didn't want to use that theory, you could plug it into the z-score concept and say, okay, well, here's my z-score. My distance between my point and the mean divided by number of standard deviations should be the z-score. My z-score here was 2, and so 2 is equal to 10 over the standard deviation. We do the same thing. We multiply sigma over. We divide both sides by 2, and so sigma should be 10 divided by 2 should be 5, which means 5 centimeters per standard deviation. Have you seen a baby? He'll be fine. All right, let's look at that one more time. Science summer exam, mean is 82 marks, and it has an unknown standard deviation. We want to find the standard deviation. So Wexler says 75% of the lowest 75% come in, and the highest grade of that group was 86. So tell me the standard deviation. So all of these people came into the science summer program. That's 75% of the data. Where's the standard deviation? Or what's the standard deviation? We're going to do the same thing. Based on this specific data, I don't know. So we have to ask the standard normal, which has a mean of 0, and I want to see where the boundary is that stops the 75% fill up. Right? So we're going to do that same thing with our calculator.
We're going to hit the second bars, inverse normal. We put our percentage in that we want the bottom up to be, and
82 is the mean, but I don't know the standard deviation, so I can't use this. So we have to kind of work backwards and say, okay, in a regular standard normal curve, what does it look like? 0.67 is where the cutoff is. So in this one, this spot is 0.67, which means that it's 0.67 of a full standard deviation above the mean. So whatever distance this is 0.67 of a standard deviation. Put that into this and say the distance from here to here is 4, that's x minus mu, divided by the size of the standard deviation is 0.67. And therefore your standard deviation is 5, almost 6. Another way to think about that is 0.67 standard deviations is this distance, which is 86 minus 82. It's the same formula, I'm just kicking standard deviations out in front by the z-score. So 0.67 of a standard deviation is 4 units wide, right? And if you want to get sigma by itself, you divide both sides by the 0.67, and you get your 6 units. It kind of makes sense, I mean, it should make sense, because if this is the mean, if you go a full standard deviation is about 6 units above. So one full standard deviation should be 6 units. 1, 2, 3, 4, 5, 6. That's one standard deviation. So that's going to be 88, right? So 88 is going to be a full standard deviation. We're not at 88, we're at 86, which is 4 out of those 1, 2, 3, 4, 5, 6. It's 4 out of those 6.
It's 4/6 of the way, if you will, which is 2/3, and 2/3 is 67%.
Which is 67% of a standard deviation. This is, I think, as hard or as challenging to put together in your mind as some of the calculus. So if you're like, cool. This is like in the top 5 of hardest things that we're going to see in the course. Okay, this is one for you to try out. Same idea. Pause me until you've run through it a little bit. Hi, nice to meet you. Sweet dreams are made of cheese. Who am I to disagree? I don't know. So 35% of the mice have whisker length less than 42. Here's the mean. What's the standard deviation? I don't know how many standard deviations that is, but I know on a standard normal curve that if this were 0 and this we didn't know was k, we could figure out how many, what the k value is by using, again, second dist or inverse norm. We want 35% and 0 and 1. 0 and 1 tell us that it's a standard normal curve, and this negative 0.385 tells us, the negative tells us that we're below the mean, which makes sense because 35%, if it was more than the mean, it would be bigger than 50%, because 45 is, the middle is 50% of the data. So this tells us that we're about 38% of a standard deviation below the mean. We have to use this idea that the distance between here and here, those 3 units, the 3 units are negative 3 units is negative 0.385 of a standard deviation. All right, and you could divide that out in your calculator. Another way to look at that is with the z-score technique, with the z-score formula. I think this makes less sense, that's why I read it like this, but here's the difference between r value x and the mean. That's this is 3, sorry, negative 3, divided by the size of the standard deviation, which we don't know, tells you how many standard deviations below the mean. I like to think of it as 0.385 standard deviations is 3 units wide, and then you divide and find that a standard deviation is 7 or 8 units long. Okay, so we want to find the mean and the standard deviation, but now they give us 2 components, right? This is the same thing as saying 10% of the mice have shorter legs than 20 centimeters, and 15% of the population have legs bigger than 29 centimeters. It's this that's happening twice. 10% of the mice are below 20, and 15% of the mice are above 29. Okay, we don't know 2 things, but what we can do is try to find how many standard deviations this is below the mean and how many standard deviations this is above the mean. I want to find the z-score for this one. All right, so I'm going to, in my calculator,
say second dister, inverse normal, I want 10%. Cool. Boom, boom.
This is negative 1.28 standard deviations below the mean. X minus mu over the standard deviation equals the z-score. 20 minus mu, I don't know mu, and I don't know standard deviation, but the difference here divided by the number of standard deviations should be 1.28. Another way you could look at it is the distance between 20 and the average is negative 1.28 of a standard deviation. There's one equation. The other equation comes from this, which is this side. And so I want to find the distance between 29 and the average. I don't know that, I don't know sigma, but I can figure out how many standard deviations above this would be if it was translated to a standard normal. So I'm going to do the same thing that we've been doing, but I can't use 0.15. I've got to use 0.85.
You guys are comfortable with this already. 0.85.
1.04, I'm going to call that. So this is 1.04. Another way to think about it is the distance between 29 and our average. The difference is almost one whole standard deviation. So now I've got two equations and two unknowns, and we can smush them together. So then we're going to try to solve with a system of equations. This was a 29, and so this should give you 9. This is plus, so plus gives you no mu's. This gives you 2.32 sigma z. And when you divide, you get 3.88. Is it right? Is it right? Voila! You take your 3.88 as sigma, plug it back into here or here, and solve for mu. Solve for mu, you get 25. That's the hardest thing in probability that they can throw at you.